Okay, so last day we were talking about nonparametric tests and how to deal with violations of assumptions. And so what I'm going to do now is continue on with that, in part to look at the tables. Then I'll talk briefly about how to do a one-sided Mann-Whitney test, and then I'll talk a little more generally about how I want you to handle violations of assumptions, at least for the purposes of the tests in this course. So in the last lecture, we'd done a Mann-Whitney U test. We were comparing the size of fungi in two forests. And because we violated the assumption of normality or heterogeneous variance, at least we imagined we had, we instead ranked the data, and then we carried out a Mann-Whitney U test, a two-sided test, and we calculated U statistics, and finally you pick the bigger one as your test statistic. So the U calc, the test statistic, ended up being 46. And remember, we had sample sizes for group 1 or forest 1 of n1 equals 8. And forest 2 had the same sample size of 8. And so what did we need to do was to look up the critical value of Mann-Whitney with alpha 2 equals 0.05 with sample sizes of 8 and 8. So we don't really calculate degrees of freedom for the Mann-Whitney U test. We simply use the sample sizes to look up values. And so let me switch to the tables if I can. So here's a portion of the Mann-Whitney U table down here. And so the Mann-Whitney U critical values are listed in the body of the table, and they're really easy to look up. Across the top you have one of the sample sizes, so n1, and across the bottom you have the other sample size n2. And in fact, n1 and n2 are entirely arbitrary. So in our example, we had equal sample sizes, so sample size of 8 for group 1, 8 for group 2, and so the critical value, as we determined before, was 51. Let's imagine you had unequal sample sizes. Let's imagine we had 5 and 10. So n1 was 5. So here's 5, and n2 is 10. So the critical value would be 42. And if you arbitrarily changed the group 1 versus group 2, you get exactly the same thing. So if group 2 was 5, group 1 was 10, so 10 is here, you get a value of 42. So they're exactly the same. So which is group 1 and group 2 in terms of looking up critical values gives exactly the same answer. So easy to look this up look up critical values in the Mann-Whitney table. The book describes what you do. What you'll notice, the sample sizes here only go up to 15. If you have bigger sample sizes than that, you need to, the book describes, but we won't cover it, how to deal with it. In fact, it involves converting it and looking up a Z statistic. So we won't do that. And in fact, as I've stated before, really what you ultimately want to do is to run all this, in any case, in SAS. And so that's what we'll do. And so SAS will run in the problem set. I've described how to run a non-parametric test. It's not exactly the Mann-Whitney U test, or it's a slightly different statistic, but you don't have to do the ranking and all the work yourself. And it, as SAS always does, it provides a test statistic. I think it actually does a chi-square of sorts, but it also gives the p-value directly, so you can use that. So you can check those details out in the problem sets. Okay, so we just looked up the critical value, and we found that it was 51. And so we've already completed this test anyway last day. Because the U calc is less than the critical value, we don't reject. That's what we had already determined. Okay, well, what do you do? How do you handle a one-sided Mann-Whitney U test? So everything is done exactly the same way. If you're doing a Mann-Whitney U, but it's one-sided, then the null hypothesis, null hypothesis is always going to be basically that whatever the thing you're doing, you're measuring for group 1 equals that of group 2. And an alternative hypothesis might be that group 1 is less than group 2. And so when you're doing a one-sided Mann-Whitney U-test, you don't calculate both U1 and U2 and choose the bigger. Which U you calculate is determined by the alternate hypothesis. Okay, so in the case where group 1 is said to be less than group 2, just calculate the U1 statistic and use that as the test statistic. So that is really what we could call U-calc, the calculated U-test statistic. If you have the opposite, so again, it's going to be a one-sided test, same null hypothesis, group 1 equals group 2. The alternative now is the other way around. Group 1 is greater than group 2, whatever they happen to be measuring. Then you do the opposite. Right? U2 is the test statistic. So you just calculate U2 and use it to compare to the critical values. So this becomes what I've called before U-calc, or the test statistic. So you look that up, compare it to the critical values. So you look the critical values up in exactly the same way based on sample sizes, but the only thing it's a sort of like a bit less work. The only thing you need to calculate is U1 if group 1 is thought to be less than group 2 in the alternate hypothesis, or you do the exact opposite. If group 1 is greater than group 2, you calculate U2. Finally, I think there's one other thing I should point out, and that just really it'll allow you to check on your calculations, and that is that this really applies more to the two-sided test, and that is that U1 plus U2 equals N1 times N2. So if you're doing calculations for a two-sided test, you can just do this quick check that you haven't blown it somewhere in your calculations. So U1 plus U2 should equal N1 times N2. So you can double check. Or another thing you could do is, once you calculate U1, you could get U2 by subtraction. But it's probably to calculate the U's separately, as I indicated last day, and then double check on your calculations using this equation here. So it's a useful thing to know about. All right, so that's the only other nonparametric test we're going to carry out. As I said, there really are nonparametric tests that involve ranking the data before you analyze it because you violate some assumption. And so there are tests that are analogous to things that we might do, like correlations, analysis of variance to compare many means, where you, instead of analyzing the raw data, you analyze the rank of the data. So there are many, many such nonparametric tests that you can use if you violate assumptions. We won't cover those, but many of the underlying principles are the same. That largely involves ranking the data and then analyzing the ranks. And there are fewer assumptions involved in these tests, so they're preferable in many cases. If you violated assumptions, you want to use one. So you can look those other ones up once you leave this course if you need to use them. Okay, so let me just tell you how, for this course, and certainly for the tests we're going to do, how I'd like you to deal with violations of assumptions. And so if you need to do an independent sample T, so in other words, if you have two samples, you want to compare the mean, they're not paired in any way, so independent sample or two-sample t-test, first do an f-test for homogeneity of variances. In other words, an f-test to see if the variances are equal or not. So if you don't reject that null hypothesis that the variances are equal, in other words, if you have no evidence the variances differ, do the t-test. If you do reject the null hypothesis, in other words, if the variances are indeed different, you have evidence they are different, then you're going to do Mann-Whitney. So unless I say otherwise, when you have data for an independent sample t-test, you should always use this approach, unless I say otherwise, unless I say don't test any assumptions. Of course, the reality is, if you, outside of this course, what you would really do anytime you had such data was you would explore, test for normality, plot the data. That's the first thing you should always do in any case. Look at a histogram or the distribution. Does it look normal? SAS will also calculate for you a test statistic involving whether or not the data are normally distributed. So that's the first thing you should do. And you should do an F-test for homogeneity of variances, and SAS actually automatically does that for you if you do a t-test. So that's how we're going to handle t-tests, right? So first, test the homogeneity of variance assumption. If you don't reject, you happily go ahead and do the t-test. If you do reject it, you unhappily, well, not necessarily, you do the Mann-Whitney U-test. And outside of this course as well, you could seek a transformation that I discussed earlier to see, and that would be the first step I would do if I violated the assumptions. But since you never know if a transformation is going to be effective at removing the violations of assumptions, it's too difficult to deal with by hand, right? You can easily do that on computer. You can explore transformations quite easily by just transforming the data in different ways until you find one that works. But for the purposes of this course, you can't really do that sitting on a test because you might be there forever trying different transformations. So that's how you're going to deal with independent sample t-tests. What if you have a paired t? So for paired t-test, the assumption is that the differences are normally distributed, but you can't test for normality of differences while sitting there at your desk. So what I'd like you to do is look for outliers, so extreme values of differences. If you see them, if you have outliers, you're going to use the sign test. Right? The sign test really is a binomial test with p equal 0.5. Just carry it out as you do any binomial test. So look up, if you've forgotten your binomial test, look up how to do it. And I, in fact, did an example last day. Okay, so that's all I'm going to say now about nonparametric tests and the handling of violations of assumptions. Although I may tangentially talk a little bit about how to deal with other violations later on, but we won't do any hypothesis tests that involve means of dealing with violations of assumptions. And finally, I guess I should add, let me just reiterate that if your data originally are not measurements, they're not measured values, but they are originally composed of ranks, you go straight ahead to a Mann-Whitney test. So an example of that I think I gave the last day, if you wanted to compare the heights, let's say you want to compare the heights of males and females, then you just take a random set of males and females, throw them all together, and you can just rank them by eye, right? You have the smallest person, then the next biggest person, and so on. Assign a rank to them, 0, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, up to whatever it is, and just analyze the ranks using a Mann-Whitney approach. Next day we'll move on and we'll begin talking about the analysis of variance, which is a general term for a general suite of tests for comparing two or more means.